and it will significantly influence the power extraction process of downstream turbines. But currently, most of the wind turbines are operated by the so-called grid strategy, so which means each wind turbine in a large wind farm just focusing on the power generation of itself, while ignoring the potential influence to all the other turbines that may be influenced by the wake induced from the upstream turbines. So we aim to mitigate this issue. We hope to control all the wind turbines in a large farm by a cooperative way. But from the perspective of control system design, the wake is a complex phenomenon and has stochastic features. And particularly, you can see wakes can interlink and they can couple with each other. And that further increases the complexity of such a control system. So from the control perspective, it's very hard to build an accurate and control-oriented model for the controller design. And so all these features block the direct application of conventional control methods designed for white boxes or gray boxes. And so in our work, we treat the wind farm control task as a possible black box due to the high system complexity and the strong uncertainty. The control of black box systems is almost the mission of impossible for conventional control methods. So for instance, think about a video game. So how should we analytically build a model for a video game, not to mention control it, right? It's almost impossible for conventional method. But we can do this by machine learning. So this is where AI steps in. So particularly, we can use booming AI technology, which is reinforcement learning, to handle the control tasks of black box systems. So reinforcement learning is AI technology induced by, inspired by the learning behavior of human beings. So as human beings, we do not need to know the models of ourselves, right? But we still can accomplish many very complex tasks. So some simple ones like walk and run. So think about how we learn to walk when we are a child. We first observe how other people walk, right? And then we take a step, and this step can be good, can be bad. We may fall down, but we can learn from such a step. It's kind of we get some rewards, no matter the reward is good or bad. But such reward can help us to improve our future movement. And by such a learning iteration, we can finally learn how to walk, how to run, right? And reinforcement learning is actually inspired by such behavior. So it's based on trial and error. So it asks a system to interact with the environment. And the AI agents gather input and output data at their observation. And they also receive a reward from the environment to gather their future control policy. So through such a iteratively learning process, reinforcement learning can accomplish many complex tasks for black box systems. And I will give you two quick examples of some recent achievements in this area. And a famous one is AlphaGo. So this is an AI agent that managed to beat some best human professional players in the game Go. And a more recent and even more famous example is ChatGPT. So it's now everywhere, right? But though ChatGPT's primary focus is about natural language processing, but what makes ChatGPT performance so much better than other large-scale models is the reinforcement learning-based inner loop. So basically, they use an algorithm called PPO, and it allows humans to judge whether the results generated by ChatGPT are good or bad. So human can kind of like marking the results for ChatGPT and feedback that to the machine. And then the ChatGPT can learn from such feedback and keep updating itself to get better performance. So how powerful reinforcement learning can be. And in our work, our initial idea is quite straightforward. We want to leverage this powerful tool and design new methods to handle the control tasks for wind farms. All right, and we started this work about almost 3 years ago. And initially, we hope to use yaw control to achieve weak steering, therefore increase the farm level power generation. And here we improved very famous reinforcement learning method, and we do some application-oriented designs, such as we designed a reward regularization module to handle the reward change under different wind speeds and under different yaw angles. And our method is data-driven and model-free. We don't need any PV, OD model for the wind flow. We just need the common environment from each turbine, and then we control the each turbine by design some controller to ensure the yaw maneuver with exponential convergence of the yaw tracking errors. Okay, and we carry out hypothetical simulation with SOFA. So this is kind of the bird eye of a wind flow. So the color means different wind speed, and you can see the small black bar there. They represent the wind turbine. And after offline training and online fine tuning, you can see after 3 online fine tuning iterations, we can increase the whole farm level power generation by around 10 to 15% compared with the previous strategy. And so this is our initial work, and after that we see some challenges in such control system design, and we hope to achieve better robustness against the different wind speeds and directions, and we also hope to achieve reduce the computational cost to enhance the applicability of our method, and we also aim to achieve better adaptability to different scenarios. For example, we hope we can not only achieve yaw control, but just as Anne has said, we also hope to apply call and teach control to enhance the performance of our controller. And we also think about, if we apply our method to large wind farm, whether it's applicable. So we think about, for large wind farms, there are several turbines added up to the wind farm or take out from the wind farm, whether our method can quickly adapt to such new scenario. And another thing, is when we do yaw control or induction control, that may induce load to the turbine blade, right? Now we must make sure that we can do a great trade-off, not only to ensure that the overall power generation is increased, but also to ensure there's no big load to the blades. And for those directions, we created a series of wind farm control methods. I will just show you 2 of them. And the first one is that we developed a robust deep reinforcement learning method. And we make some theoretical achievements in this design. So we combine robust control with reinforcement learning. And we created a new network structure, which we call destructor neural network. So the function of it is to estimate the worst case scenario under disturbance. So therefore, the estimation result of it can be feedback to the controller to help the controller improve the control policy. And we also designed a special sampling strategy to enhance the learning efficiency of our method. And so here is the simulation result. So the blue line is our method, and the red line is from DDPG. The DDPG is a directive algorithm from the fundamental one used in AlphaGo. You can see under the influence of this disturbance, we achieved really better performance than DDPG. And we already applied this method to the control of the farm. And another thing is that when we apply reinforcement learning methods to wind farm, we noticed that for such a large wind farm, when the total turbine number increase, the computational cost can increase exponentially. So that could be huge if we have 100 wind turbines. So we think about whether we can, reduce such computational costs, and this motivated us to generate a so-called automatic grouping strategy. So we hoped to, by analyzing the aerodynamic interactions between different turbines, we hope to divide a large wind farm into several small turbine groups, right? And thirdly, we just need to apply our algorithm to each turbine group. So therefore, we avoid to implement a very complex algorithm to the entire wind farm. So that can reduce the learning stability and the learning efficiency, because when turbine number increases, the state and the action spaces also increase significantly, right? And our idea, one of the key ideas behind our automatic grouping strategy is the definition of the influence factor and the influence field. So it's quite, it's actually straightforward. So what is influence factor? It's just the weighted wind speed deficit under different operation mode of a turbine. So you can see this is the distribution of the influence factor of a wind turbine I, and you can see the color, the darker the color, the higher the influence. So this turbine J can be seriously influenced by the wake of this turbine Y, while this turbine K also influenced by the wake of turbine I, but the level is much lower, right? And then based on the influence factor, we defined the influence field. It's just, we put a threshold for the influence factor, and then we get the area. And you can see from the envelopes here, so each envelope indicates the influence area of after a certain threshold. And if a turbine J is within the influence area of a turbine I, we can see they are strongly interactive in terms of the aerodynamic relationship. And so based on that, we can divide the whole wind farm into different groups. And here we also employed some other technologies. The first one is graph theory, and particularly the tree structure. So we use tree structure to label, to store, and to update the aerodynamic relationship between different turbines. And then we use the depth first searching to divide a large wind farm into different turbine groups. And in each turbine group, the interaction level between different turbines are very high, but when closed group, so such interaction level is relatively low. And we also use transfer learning. So we try to exploit as much as possible from the old learning results. Therefore, when wind speed changes, when direction changes, our automatic grouping result changes. But with transfer learning, we can quickly catch up the new scenario and get good control result under the new conditions. And we also employ the multi-agent design to bring some extra training flexibility for our method. Okay, when we combine all the things together and also with reinforcement learning, we developed a new algorithm basically. And I will show you some simulation results. So we carried out many simulations for large wind farms with turbine numbers ranging from 30 to 80. And the left-hand figure shows that our method can achieve clearly better power generation compared with the grid strategy. So here, this gamma is the wind direction. So we keep changing the wind direction. And from the curve, you can see the wind speed is stochastic. And so this yellow line, this yellow curve is the power generation from the grid strategy. Of this blue line is our result. This red line, the benchmark, is based on a pure reinforcement learning without any grouping strategy. The left-hand figure, you can see with our method, we achieved a very similar performance compared to the case without the grouping strategy. But in terms of the training time, we can reduce the overall training time by over 80%. So we believe this is a good trade-off, and this kind of this kind of lays the foundation for the application of reinforcement learning to very large wind farms.
What is on the y-axis?
I'm sorry, who's this one? So this is the percentage is the training time, is like second. So this 100% is, is from the pure reinforcement learning without any grouping strategy, and this is our result. So you can see we reduce 80%. Okay, and so this our work about wind farm control, and I want to mention that many of our designs are generic and can be applied to many other systems, such as wave energy converter, wave turbine, and also autonomous systems. I will show you two examples. So the first one is the single turbine pitch control. So here we aim to handle two different objectives. The first one is, of course, power regulation, and the second one is load efficient. And so here we use model-based reinforcement learning method, and so I believe this spider figure can clearly show the result of our method. So those are different bending moments. So we calculate the dynamic equivalent load for them under different controllers, and the green lines are the result of our controllers. Well, you can see we achieved the smallest bending moment from every aspect. So this means by using reinforcement learning, we can not only achieve high performance power regulation, but also mitigate loads. And another quick example is the control of wave energy converters. So here we apply reinforcement learning to try to extract more power from a wave energy converter. And the special design here is that we can incorporate the future prediction data of wave. And the figure here can show the performance of our results. So this is the cumulative power extracted by the wave energy converter. And the red curve here is from our design. So you can see with time going, we get more power than many other methods, including a very commonly used, very famous model predictive controller. We achieved like 20% increase in this case study. And I also want to mention that, including this one, many of our reinforcement learning designs definitely not just the simple application of existing methods to new systems. We made quite a lot of theoretical designs and application-oriented designs. Such as for this one, we create a special preview structure in our algorithm. And this structure can help our algorithm to adapt to different wave profiles. We tested our algorithm with quite a lot of wave profiles, and it's all performed well. Well, some other reinforcement learning algorithms failed in some wave profile, such as under some extreme condition or some wave conditions that far away from the training set. And another thing is that we have quite a lot of flexibility in our design. We can make our algorithm model-based or model-free. So sometimes we can use some physics information to enhance the learning efficiency, and sometimes when it's very hard to get a model, we just do the work from the hardware. And another thing is that when mentioned about reinforcement learning, I know many people's first and also initial concern about the high computational cost, right? So this is not always the case, but we always try to mitigate this issue. Such as for this one, we can carry out offline training. So the dirty job was done offline, and then we apply it in real time to achieve closed loop control. So when we apply it online, the computational cost in terms of running time is much smaller than that of MPC. So I think so that can prove this method is applicable. And here are some references that cover the topics I talked today. And I want to use the last two slides to talk about our future work in this area. So recently, based on our results in both digital twinning and also control, we get a 6 million euro project, which is titled Smart Aware Integrated Wind Farm Control Interacting with Digital Twin. And here, boosted by this project, we hope to significantly expand our current results in both digital twinning and controlling. And we also hope to combine them together and cover more complex tasks, such as we hope to do digital twin from the component level for bearing system, for the drive train system, and also then for turbine level, and also for control for turbine level, and then for farm level, and finally even the cross farm level. And eventually we hope to develop an integrated wind farm management system powered by AI. And we aim to achieve tasks also for different time scales, such as real-time control and medium-term decision-making, and also the whole lifetime management for the turbine wind farms. And in this project, we gathered 7 academic partners and 7 industrial partners from 7 Europe countries. And we plan to do various experimental tests, such as we plan to do tests with the national level wind tunnel at Imperial, and we will also do site tests with a commercial wind farm at Belgium. Therefore, we can significantly boost the, as Dr. Jia mentioned, the TRL level of our strategy. Yeah, okay, that's pretty much for today. Thank you very much for your attention.